Welcome back. The objective of this video is to evaluate the summation and find the limit of a summation as we close in on our area problem. So let's take a look at example 2 and evaluate the summation. We want to evaluate the summation of I equals 1 to n of I plus 2 over n squared, for n equals 10, 100, 1,000, and 10,000. Our solution here is to begin by applying the summation formulas and properties to simplify. In the second line of the solution, note that 1 over n squared can be factored out of the sum because n is considered to be a constant. We can't factor out I because I is the variable and the index of the summation. So let's take a look at this. So S equals the summation of I equals 1 to n of I plus 2 over n squared. So we do see n squared as a common factor, or 1 over n squared. And so we can factor that out and place that as a multiplier on our sum. So now we just evaluate I plus 2. So now we can write this as two sums. The sum from 1 to n of I plus the sum from 1 to n of 2. And for each of these sums, we have a pattern from objective 2. So if we look at objective 2 and we see our notes, we can apply formulas 1 and 2. So we have 1 over n squared, and our formula from objective 2 of I is n times n plus 1 over 2, and our constant 2 is just 2n. A little bit of multiplication. We distribute the n. We'll need a common denominator here with 2n. We need a common denominator of 2, so we multiply that by 2 over 2. So we get 4n, and we end up with n squared plus 5n over 2. I'm going to go ahead and factor out the n in n squared plus 5n, leaving me with n times n plus 5 all over 2n squared. And the n in the numerator will simplify with one of the n's in the denominator, so we're left with n plus 5 over 2n. So we can note that the sum appears to approach the limit as n increases. To find the limit of n plus 5 over 2n, we simply apply our concept of what happens as n approaches infinity. What happens as n gets really, really large? Well, as n gets large, the 5 doesn't matter, becomes the battle of n over 2n, which just simplifies to 1 over 2. So this strategy is a lot more effective and more efficient than evaluating these separately as sums. It's much more efficient to convert to the rational form here of n plus 5 over 2n and simplify that and find the limit, as opposed to doing each of these individually. So with the rational form, each sum can be evaluated by simply substituting appropriate values for n. In objective 4, we want to find the limit of a summation. So we want to find the limit of s sub n as n approaches infinity of this particular summation. So the sum from I equals 1 to n of 1 plus I over n quantity squared times 1 over n. As we did in the last problem, we want to rewrite in rational form. We've got our original form of the summation. We can FOIL this out or multiply this out, use our patterns, and get a common denominator, and we end up with n squared plus 2ni plus I squared all over n squared times 1 over n. Multiplying this, we can take out our common factor like we did in the previous sample. Our common factor here now is 1 over n cubed, so we factor 1 over n cubed out of the sum. And now we can evaluate and look at our three different sums. So the n squared sum, the 2ni sum, and the I squared sum. Well, the sum of 1 plus, or I equals 1 to n of n squared is just n cubed. And here we can factor out our constant of 2ni, and our I, looking at our properties from earlier in the video notes, I is n times n plus 1 over 2. And then the sum with I squared from earlier in our video notes is n times n plus 1 times 2n plus 1 over 6. So we use our summation formulas from objective 2. So all this stuff here. So each one of these, we have our 3 different terms, our 3 different summations. Now, an algebraic miracle occurs. We are going to distribute the n into the n plus 1. We're going to FOIL all these. We have to simplify each one of these 3 terms individually. So by multiplying, distributing, and applying a common denominator, because these terms all have different denominators, 1, 2, and 6, so we need a common denominator of 6 to add all these together. So you will need to do that. And that all is going to simplify down to 14n cubed plus 9n squared plus n all over 6n cubed. Now that we are in rational form, we can find the limit as n approaches infinity. So as n approaches infinity, it becomes a battle between our highest degree n's, and 9n squared isn't going to matter, n isn't going to matter, so we simplify 14n cubed over 6n cubed, it's an n cubed. These guys battle to a draw. 14 over 6 simplifies to 7 over 3. And we'll get some more practice with these when I see you in class.